Hello again. We're going to try another problem with a spring. Essentially, this is almost simple concept in physics called simple harmonic motion. I'm going to talk a little bit slower this time. But we are going to calculate for the speed using the conservation of energy, and that's for without friction. But with friction, we're going to use something else. Okay, so it's a nice, good comparison with or without friction, and which physics principles or laws, in this case, that you're going to use to help solve the problem. In this case, the same thing: the speed of the block as it hits the spring, or at a certain point. Okay. I erased part B because it's almost irrelevant at this point. I don't know why they asked for the speed midway, but we're just doing A and C for comparison. Okay, and for these problems, the free body diagram is given to you. That's nice. Helps you know the direction of the forces. And also, you'll need the normal force for friction later on, but not for the first part. Let's try this out. Also given a strategy there. That's fine. Given the mass, oddly enough, we will not. Yeah, we'll need the mass for sure. Shortcut. Still pretty heavy spring. The initial position of the block is away from the equilibrium position. Okay, and then for part, this is for part A. That's my color. For part B, it introduces coefficient of friction. Okay, so not that bad. Unitless. And our goal is to find essentially VF at the equilibrium position with and without work done by non-conservative force like friction. Okay, and so check this out. There'll be a whole slurry of formulas that we'll need, but the basic ones that we'll need essentially are these. Okay, this is the law of conservation of energy. Shortcut. And an extended version of the work energy theorem. Principle. I like to use theorem. Okay. We'll also need some other formulas as well to note that kinetic energy squared, elastic potential energy. Take note that this is on just a level playing field. There's no change in height, so we will not even need the formula for gravitational potential energy. As a matter of fact, we'll also need friction. Okay. And for good measure, we're going to need that one as well from past chapter. Excellent. So how does that all come together now that we have the ingredients? Almost is like a recipe. Please forgive me, I was just watching a cooking show earlier. So let's see where we can start with. Obviously, we're going to start with A, the frictionless example, and we are going to start with the law of conservation of energy. It states that energy cannot be created nor destroyed, but that essentially mathematically means that the sum of all the energies beforehand, after a certain event, we call the sum of all the energies afterwards, too. Okay? And also, we can split this up into kinetic energy, potential elastic. I'm going to include that's initial energy final. Okay, but take note, what is our y position here and final, especially at 0? So that's just going to go away, that term at least. And so we're just left with even there's going to be more terms that will go away from this as well. Okay? Because before, and actually that should be part of the given, right? It starts off at rest. Because rest. And afterwards, at the x equals 0, that term goes to 0 as well, because remember it's 1/2 kx squared. So if x is 0, then that will go away. And you can see how it very nicely simplifies the problem. I encourage the students to start with the basic principle and then use the understanding of what's happening. There's no change in gravitational. Well, you don't even need to do that. It's at rest beginning, and then it goes back to its equilibrium, the unstretched position. So let me write that word there. Unstretch. That's where we even set our x equals 0. Okay, algebra. Okay, and remember we're looking for this. The 1/2s also cancel out. Okay, so I'm going to do a 2 for 1. I'm going to divide both sides by m, since we're looking for VF, and take the square root of that. Okay? Boom. That results in square root of kx, I forgot, that's xi, over m. I would say that you need at least to know that what position that was, the beginning or the end. Then plug and chug. 0, 5, the mass. Okay, once again, the units should also resolve out. Okay, I have Newton meter on top, and then I have kilograms. So notice that this cancels out, and then the Newton meters per second squared something's not right here. Okay, the kilogram cancels out. I'm missing something. I think it's the squared in there. There we go. So that's a good thing. Just cancels out that, not the m itself. And how did I know that? It's because of the square root. I know I should have a meter squared, second squared in there to give us the unit of meters per second, which is exactly the units of what I'm looking for. Okay. Okay, and sure enough, that gives us a speed, and we're talking about scalar quantities here, but according to our diagram, it is going to the left. That does not matter in this case because it is and this is without friction. Okay, so I'm going to pause here for a little bit to note that if this is the final speed without friction, so with friction, do we expect it to be faster or slower? Okay, think about that as we go ahead and solve our next the next part.